conduct an experiment. That's not possible. You'll conduct on a big wing. You will have at the most of 10 sensors. That means you are getting the data point at those points, 10 points. Whereas, whatever the data that you are trying to estimate in between those two sensors is only extrapolated data or interpolated data. So you use either extrapolation technique or interpolation technique to obtain the data that is not being actually extracted from the experiment. Okay, so that information is not available in the experimentation process. Whereas in the simulation process, you get the entire field data point by point. So as the number of points you increase, and that now you look at the scale. Here also the scaling comes here. If I want 100 points, I can take 100 points data. If I want 1,000 points, I can have 1,000 points data. If I have a million points, I can have million points data. So the number of points, the data obtained with the simulations would be enormously large when compared to a given experimental setup. Repeatability, and this is one of the most important feature of any experiment. Suppose I do an experiment, and I would like today I do an experiment, I get a data, and I reconduct the experiment without changing anything in that experimental setup. So, and I observe the data. If I don't get the data identical, it's not that it's highly dependable that you get a repeatable data in a given experimentation, because we don't know how fluid behaves and what happens in a given experimental setup. It is all in the external factors that are available there. Whereas the repeatability of all the parameters that you are looking in a given experiment is possible in a simulation. As I said, some experiments are tedious to construct. They're also dangerous enough. So suppose you might have, everybody might have had this information that a few years back, 2 to 3 years back, there was a large explosion at Indian Institute of Science wind tunnel lab, and there was a few researchers who are doing. Some of them have passed away, as well as some got serious injuries, and the entire setup got collapsed. Okay, so it's dangerous. That's not a great experimental setup, but that's a dangerous experiment, because it involves high compressed air. That's it, nothing else. There is no explosion. There are no explosive materials that are involved in that experiment. But in fact, that experimental setup got exploded, and it costed human lives. And there are many places where experimental setups are dangerous. Whereas in the simulation, we can say that such a kind of dangers can't happen in the case of simulation. So if you look at these 6 parameters, with these 6 parameters itself, we can see that how a numerical simulation can overcome experimentation. But now we ask the question: are the numerical simulations reliable here? We can say that they are reliable, but the experiments that you do, that is the truth. That is the ultimate truth. It's like visualizing God. So that's the truth that you're looking. The physical. If you have a carefully designed experiment, and if you get a data out of it, that's the best data that you can get from any of the sources in that experiment. So that is the ultimate truth that you have in the experimentation. You can't replace it. But from the simulations, we can go to as close much as possible to that truth. That's the limitation that we have in the case of simulations. So with these small number of parameters, we can understand that how numerical simulation would help a large amount of would reduce a large amount of time, money, as well as safety features that we get in a given from a given experimentation. So this is why we need what is called a CFD. Then we would like to look at. Okay, I understood. I could see what is the definition of what a CFD is, and why do I need CFD as a whole. But we would like to ask the question: what are the basic flow features that we will be resolving? Okay, so let's look at it. Most of the flow fields can be classified something like this. They can be classified based on Mach number. Mach number, some of you might have not known it. It's a non-dimensional number which gives a ratio of the fluid velocity to the velocity of sound in that medium. So it's a ratio of 2 velocities. fluid speed, the physical speed of the fluid, to the speed of sound in that particular medium that you're looking at, whether it is water, fluid, any fluid that you're looking at. So if the Mach number is less than 1, if the Mach number is less than 1, we call it subsonic. The sonic means if the fluid velocity and the speed of sound is moving with the speed of sound, we call that state to be a sonic speed. So if it is less than 1, it is subsonic. If it is in between 0.8, if the Mach number is in between 0.8 to 1.1, we call it to 1.1 and 1.2, we call it to be in a transonic region. If it is greater than 1, we definitely call it to be a supersonic region. And if it is greater than 5, it is hypersonic region. So an object that is moving with, now you can have a fluid that is an object moving relative to the fluid in all these on this ways. You can have subsonic flow. So suppose you are moving in a bus, or you are going in a on a bike, or you are going in an airplane, or traveling in a train. So all these things are moving objects with respect to air. So their speed, the speed of sound in air is about 330 to 340 meters per second based on the temperatures. And you see that if you take the object velocity to the ratio of the fluid, the speed of sound at that point, you'll see that most of the objects are subsonic in nature. But don't you have where are the other three regimes that are available? Transonic region, yeah, there are when you are flying in an aircraft. If your aircraft is at a speed moving at a speed which is closely between 0.8 to 1.1, we call that to be the flow over there. It will be transonic. And you can have fighter jets moving at supersonic flows, as well as all these rockets and re-entry vehicles and certain fighter aircrafts, they move at hypersonic speeds. So we can have objects having flow. There is a wide variety of flow features that can happen in these four. That's with respect to Mach number. Then with respect to time, if you see, you can have flows which are unsteady in nature, which are steady in nature. Then based on viscosity, if you look at it, the flow can be classified as inviscid flows, where the viscosity is assumed to be 0. See, viscosity is a fluid property, it's a physical property of the fluid. Every fluid that exists in the earth, in this universe, has certain amount of viscosity. But there are certain regions in the flow field where viscosity can be neglected. Okay, so those areas, in those regimes, we can consider the fluid flows to be inviscid. In most of the cases, it would be viscous. So you have inviscid flows, you have viscous flows. Then you have flows classified based on Reynolds number. Based on Reynolds number, you have a flow which is laminar in nature, transition in nature, and turbulent nature. Laminar flow is generally an exception. Most of the flows are turbulent in nature. Laminar is only kind of exception. And transition flows are one where you have a laminar flow and it is moving towards a turbulent flow. So that region where it is transferring from laminar to a turbulent is called transition flows. They are called transition flows. And there is no fixed Reynolds number based on which you can say that. It depends on the flow field where you are looking at. Suppose if you have a flow through a pipe, or incompressible flow through a pipe, and if the Reynolds number is less than 2300, then we can consider to be laminar flow. But it is not strictly saying that it is valid, that 2300 number is not strictly valid for all kinds of flows. So if you look at flow over a sphere, at Reynolds number 50, that flow can be turbulent. Okay, so there can be, depends on the fluid and the speed at which the fluid is happening. You can say that the flow can be classified as a laminar, transition, and turbulent. Then you can have one-dimensional flow. One dimension in sense, it's a unidimensional flow, 2 dimensions and 3 dimensions. Then you have buoyancy-driven flows based on forces acting on the fluid. Now, when you say forces acting on the fluid, we know that those who are learned from fluid mechanics background, you have forces which are acting on the surface, you have forces which are acting on the entire body of the fluid, basically surface forces and volumetric forces. Apart from those things, you have buoyancy-driven flows where density gradients impart the flow fields. This you can see if you take an empty bowl, keep it on a stove and heat it. You see that initially there is no movement of air in the empty bowl. The bowl is completely empty, and after some time, as you keep on heating the bowl, you see that you fumes coming out of it. That fumes that are coming out of it is because of the density gradients that have been created because of the temperature, the heat that you are giving to the system. So there are places where buoyancy-driven flows are important. There are places where gravity imparts the flow, like in rivers. Rivers, you see that it's an open channel where the pressure is uniform everywhere. It only the flow of river happens only because of the sheer gravity. So the amount of gravity force that is happening, that is present there, would create the flow fields. So there are and you have combination of all these things. You can have unsteady transonic inviscid flows, unsteady viscous hypersonic flows, or turbulent laminar, the turbulent viscous hypersonic unsteady flows. So combination of all these parameters would give so many flow fields. So there are huge categories of flow fields, and we would like to understand what are the ways in which I can simulate all these kinds of flow fields on a computer. That's the whole point of what is called CFD, what CFD does. So when I was talking about supersonic hypersonic flows, the flows, you can see that flows will have certain amount of singularities that are available. So I'm going to explain here you a simple experimental setup. This experimental setup, this is called a shock tube, where you see that the shock tube is nothing but a simple pipe. Okay, assume a pipe, and at some point in the pipe you have a diaphragm. That is, you are blocking the pipe with a thin metal, say metallic sheet. And one side of the pipe you have a fluid which is filled with, which is at a higher pressure. And the other side of the diaphragm, you have a fluid which is at a lower pressure. So as shown in the figure, which is given as initial conditions. So this is the initial setup. So I have a pipe blocked at one point, and you have a high pressure fluid in one side, and there's a low pressure fluid on the other side. This is at t is equal to 0. You are assuming that that's the instant that you are looking at it. Now, if you instantly rupture the diaphragm, what happens to the flow field in that? So this is what happens. If you see on the right hand side, you have a wave called shock wave that happens to travel from left to right. A shock wave is a wave which is a compression wave, which compresses the fluid ahead of it. Okay, it moves. It's a wave which compresses the fluid ahead of it. And all the properties across the shock wave, various discontinuities, we'll see in that manner. We'll see that in a moment, right? So we'll understand that as the diaphragm ruptures, you have the following waves happening. So from left to right, you'll see a shock wave traveling, and from right to left, from the same diaphragm, you'll see a rarefaction traveling in the opposite direction. So you have an opposite wave called rarefaction traveling. You have a shock wave that is traveling in the front. And in between these two things, there is a contact discontinuity wave that is sitting there. Okay, so as you rupture immediately, you'll see that the variation of density and pressure would be something like this, as you're seeing on the plot. Okay, so I'll show you a simple animation over here to understand what this is. Can you see the presentation animation over here? Is it visible?
Yes, sir. Yes, sir.
Okay, so I'm replaying it. So initial condition, it is something like this. So you say that there's a diaphragm that is getting ruptured there, and as I play it, you'll see that there's a one wave moving from left to right. There's a one other wave that is moving from right to left. But here you don't see, in this plot, you don't see a contact wave that is sitting there, because this is a plot of pressure that I'm showing you over here. Okay, this is the numerical simulation that I'm trying to show you. But if I have to show the same thing for an experimental setup, I may not be able to do it. I may not be able to visualize the shock wave as simply that I'm showing you here. Okay, let us look at the same thing in terms of pressure. What happens? So initially there was you can see that. So this is the shock wave that is moving, and this is the contact wave that is moving, and this from this point to the left hand side, it's a smooth region, so it's an expansion wave. So this is numerical. This is the data obtained from numerical simulation. Now if you observe this pressure and the pressure plot that over here, you can see that the density plot, the one that I've shown is a density plot, and the density plot shows similar structure as I'm showing in this figure. So now we have to understand that the experimental setup was very simple, but it involved a gas which was at higher pressure at one region, and from that region there is a lower pressure region, and you see that there are different waves that are emanating from that particular point as the flow field starts to evolve. Okay, so that's the main concept that we need to understand. Now let us look at what happens to these waves. So as I said, we have shock waves moving from left to right. We have rarefaction wave moving from right to left, and there's a contact surface that is sitting in between. Okay. Now let us analyze each and every wave that is available there. Look at the shock wave. A shock wave is a wave where all the properties in that fluid will have a discontinuous jump in the flow. That means you have a jump in pressure, you have a jump in density, you have a jump in velocity, you have a jump in temperature. Every property, whatever the property that you want to conceive in that particular fluid, every property will have a discontinuous jump, and the thickness of the shock wave will be of the order of few micrometers. Okay, it's a very thin line. That's like compressing the air without a compressor. So you can imagine now compressing air without a compressor. Okay, there is no mechanical part that is available, but using a shock wave, you can actually compress air. So this is a process. This wave satisfies the entropy condition. We can look at all these details a little bit later, but it satisfies a Rankine-Hunter condition also. These are the two conditions that this wave satisfies, and this is a very important wave. People are doing so much of research in that, and it is used for biomedical applications and all those things. So this is a very important wave that you look at it. The second wave is a contact discontinuity wave. A contact discontinuity wave is a wave where only certain properties will have a discontinuous jump and certain properties will remain constant. So suppose pressure and temperature can have a discontinuous jump and density remain constant, or density and temperature can have a discontinuous jump and pressure remains constant. And it also satisfies Rankine-Hunter condition. The governing equations where you can describe these waves are called generalized Riemann invariants. These are the buzzwords I am giving to you. You don't need to worry about it. You can actually get this to know about these things a little bit later. And it also satisfies the entropy condition. And the third wave that we are talking about is a wave which is having smooth variation. So waves where the properties vary very smoothly. That's called expansion fan. Okay, this situation you can actually imagine on a physical highway. So suppose that you are moving on a highway, okay, a freeway where objects are traveling at a higher speeds, and you have a traffic light there. So when you have a traffic light, what happens is every other vehicle will come in to stop there. Okay, so that is the initial condition that you are looking at, that the high pressure region kind of thing. As you release the light, that means if you traffic light turns from red to green, what happens? There is a certain wave that if you observe it as a wave pattern, each particle of the wave is fluid is moving. So if you consider each of the vehicle in that on the road as a particle of the fluid, you will see that everything is moving forward. Okay, and you will see that the information, if you look at that as an information, there is a thin layer of information which is moving forward. And if you see that, if you draw a thin line over there, and assume that everything is moving uniformly, you see that with to the left of the line, you'll see all density of the vehicles are high, and to the right of the line, the density of the vehicles there is no density at all, basically. Of course, one or two if you can assume that. Okay, so that's called a shock wave. So the shock wave is moving in that direction. Now, if you see that, at the end, you can see that people will keep on starting the engines. That means the information is propagating, saying that there's a green light over there, and everybody starts engine afterwards. Assume that initially all the engines are switched off. The first line will start the engine and it will move forward, and you'll see that based on that, noise, if you assume that the sound that is coming from the first engine is the information that is being propagated backwards, you'll see that everybody starts engine at that point of time. So that's a rarefaction wave that is moving, and everybody does it very fast. So you see that the velocity with which the information propagates towards the right in the rarefaction wave is high, whereas the velocity with which the information propagation, that is the vehicles moving in the front, is less. So that's the information that you see in a traffic wave. So you can see the same phenomenon in a traffic wave. There's one more example that we can give at this point of time. So suppose you are all the vehicles are moving at a uniform speed. Suppose that at some point suddenly there is an accident that has happened. What happens to the immediate vehicle that is behind that vehicle? It will crash. So there are certain region of vehicles, they crash into one and to the other. That crashing zone, if you consider that crashing zone, that zone is called your shock wave. And once if you see that if this freeway, if you consider to be a long curve, and you can observe what's happening there, and you see that there's a sequence of red lights that if you observe that everything is a car that is happening there, and you would observe the tail lights of all the cars, you'll see that the red lights of all the cars, tail lights, is traveling, is sending you an information saying that there's something happened over there. So that's a rarefaction wave that is happening there. So you can see shock waves, you can see rarefaction waves in a regular on a regular scenario basis. So these are the primary, these are certain waves that we can see as the fluid flow happens. And believe me, they happen as the flow happens. Body is moving inside the flow field. Suppose you fire a bullet. Nowadays, if you can see all these things in movies, you see that the waves from the bullet it can be visualized properly in the animations that they show. So those are basically shock waves, and you can see expansions, everything that are available. So these are basically called classical waves that are available over here. Then we have what are called non-classical waves. These non-classical waves, what happens is they have the exact opposite behavior to the classical waves that I have explained. So wherever expansion has to occur, you can have shock. Wherever shock has to happen, you can have an expansion. So there's a combination of these two things that happens, and this happens very close to liquid vapor in the region where the saturated liquid vapor coexist. Okay, so these are called classical waves. I will not go through the details of this. And we have other interesting phenomena that happens in a flow field. So the other phenomena are, you can have boundary layers, you can have different kinds of structures in the flow field that you see occur. Like you can see the large eddies and smaller eddies that are over here. So these are the structures that are available inside the flow field, which we need to which would like to understand why these structures get produced, what happens to the boundary layer as it is moving. And you can also have, say, multi-phase flows. Suppose you have gas entertained by a liquid, or a liquid entrained by a gas, or you can have annular flows. So these are the few examples that I'm giving where CFD is very much important. All the methods that we are going to discuss would be applicable. So these are the some flow features that we would like to look at when you are doing CFD. Okay, now we have seen, the thing we have seen is what kind of flows that can occur and what are the flow features that we would like to resolve. And to understand these flow features and the structures, we can't talk English like this. We need to have a language where we can express all these things, and we make our tool computer to understand these equations, this phenomena that we are looking at. So we would like to look at what are the governing equations that we have. So any physical phenomena that you are looking can be classified as an ordinary differential equation or a partial differential equation. So whether the simplest equation, you take velocity. Velocity is what? The rate of change of displacement. So v is equal to dx by dt. It's in one dimension, it is an ordinary differential equation basically. But if you look at it in a 3 dimension, it becomes a partial differential equation. So every physical phenomena that you want to explain, when you are doing mathematics, when you are looking at mathematical equations, they come under the form of either ordinary differential equations or partial differential equations. So we are inevitably looking at partial differential equations, and we need to classify these equations. So if you write a general form of a partial differential equation, as shown in equation 5 over here, you see that these equations, this equation can be classified into 3 different forms. As I classified the flow features, now I am classifying the equations of the flows, basic equations, the mathematical part. I am not clubbing the physics part. I have an equation. I would like to know whether this equation falls into any of these categories. So we have three different kinds of equations, basically elliptic, parabolic, and hyperbolic. Okay, this you might have studied from geometry perspective. Elliptic curves, parabolic curves, and hyperbolic curves. The same concept is applied to partial differential equations. You see that the coefficients of the second derivatives of u, a, b, and c, and you find a discriminant of that. And if the discriminant is less than 0, it is elliptic. And all equilibrium dominant problems like steady state heat transfer problems, steady state diffusion problems, all these things, or any steady state equation that comes under the category, whether it is from fluid or from solid, whatever the domain that you are looking at, if it comes under the category of equilibrium problems, then we call them as elliptic equations. Basically, you are looking at a solution of Laplace equation from a mathematical point of view. And these elliptic equations have no preferred directions. That means to say that if you see the figure C here, every point in that domain is influenced by every other point inside the flow field. Okay, so if such a phenomena exists inside the flow field in a mathematical equation, then we call it to be an elliptic equation. And the second category of equation is a parabolic equation, which is unsteady phenomena. Suppose you have an unsteady phenomena that is happening, something which is evolving in time. So any phenomena which is evolving in time can be classified as a parabolic equation, whose from a mathematical point of view, you can say that the discriminant is becoming 0 over here. And you have the other category of equation called hyperbolic equation, where only preferred directions are available. So you can say that the directions are preferred, and within those directions you will see the phenomena is denominated. So where here for the discriminant should be greater than 0. So mathematically you can classify this category of equations as elliptic, parabolic, and hyperbolic equations. Okay. Now let us look at the flow equations. So our fluid flows are governed by basically three different equations. The first one is a mass conservation equation. The second one is a momentum conservation equation, and the third one is energy conservation equation. These three equations are, I think, known to every student that is who have come to engineering. There is nothing new in this. Only thing is the representation of these equations have changed a little bit. The mass conservation equation says that the mass entering inside the control volume and the mass in a given system should remain constant. There should not be production of mass or destruction of mass. We know this from high school. We have been seeing this. The second one is the momentum conservation equation. This is nothing but your Newton's law. Okay, you say that the rate of change of acceleration, rate of change of velocity of a body is equal to summation of all the forces acting on the body. Okay, now the body that you are looking is the fluid here. So the left hand side of this equation represents your acceleration. Don't get panicked by looking at this equation. That's just an acceleration over there. The right hand side that you have is all the forces that are acting on that body, on the fluid that you are looking at. The third one is your first law of thermodynamics. First law of thermodynamics says this: energy is not neither created nor get destroyed. It changes from one form to other form. Okay, so I'm just replacing these equations, rewriting these three laws: the mass conservation law, the momentum conservation, that is Newton's second law, as well as the first law of thermodynamics in a different form. That's it. And if I say that these equations, with respect to some other additional constitutive equations, which I'm going to show in the next slide, are called basically Navier-Stokes equations. Okay. So in these equations, if I neglect viscosity and heat transfer terms, then I get what are called Euler equations, which are shown in the 7. Again, they actually, when I say and I'm neglecting viscosity, the ideal assumption that we do in engineering mechanics is we'll neglect friction. Okay, viscosity and thermal conductivity represent a kind of friction in those domains. So if you neglect friction, these equations can be written in what are these equations are written, and they are called basically Euler equations. So you have equations written for the basic the governing equations. So we would like to look at how do we solve these equations. Okay, that's the main concept of computational fluid dynamics. and these are not pertaining to any particular fluid. They are valid for any all the fluids that are existing in nature, and the form of these equations might change a little bit here and there based on the assumption that you are looking at. Okay, so that's a thing that that's a major change that you get. So apart from those equations, now if I go back and look at this, the first equation, as I said, it is a mass conservation equation. It solves for density basically. Okay, so that's the equation you are solving for density. The second equation is a momentum conservation equation where you are solving for velocity. And the third equation is an energy equation where you are solving for basically temperature. So when you are solving energy, the basic parameter that you are looking at is the temperature. So you have density, velocity, and temperature. But you see that there are more number of parameters. You have pressure sitting in equation 6 and equation 7. There's no equation for pressure. How do you solve it? So what happens is, in mathematics we call this a closure problem. We have more number of variables when compared to the equations. That's a classical closure problem. To close this thing, we have what is called equation of state. So we write equation of state, which is the function of P as a function of density and temperature, or function of density and internal energy. And using these additional equations, we will be mathematically closing those Navier-Stokes equations or Euler equations. So with the help of equations 8, equation 6 and 7 gets closed, and we'll try to solve those equations numerically, and we get some data out of it. Okay, so these are the basic governing equations that we have, and those governing equations have certain dimensions associated with it. So if you want to solve any mathematical equation, we know that from the equation homogeneity perspective, the order as well as the dimension should get matched. So we'll try to non-dimensionalize those equations. So we non-dimensionalize those equations and with certain basic parameters, and we see that we get a set of equations which look as the original equations, but with certain additional numbers like Reynolds number and the Mach number and Prandtl number sitting in it. These are the non-dimensional numbers. So instead of changing many parameters, I would like to change these few parameters and get the same effect as all the parameters that I'm looking at. So non-dimensionalization would give that. So I have the governing equations which are dimensional form. I rewrite the equations in non-dimensional form. Now everything in that particular letter that is sitting there. So you have rho. There's no previously we call it to be density. Now you don't call it to be density. It's a number there basically. So these equations doesn't have any dimensions. It just represents some numbers. So you have mathematical equations which are valid across numbers. So you should be able to mathematically easily solve these equations. So you write those equations in non-dimensional form, and then non-dimensional and integral form. So every equation you see that is in integral form. So those people who have gone through a subject called thermodynamics have studied the concept called system and control volume. Okay, so if you have a control volume, you can apply these equations directly to any control volume that you are looking at. So integral form represents the equations which are written in control form, control volume perspective. And suppose I want to get these equations at every point inside in a given domain, then we rewrite it in terms of differential form. So the same equations I'm rewriting them in terms of differential form over here, and then say that these equations are valid at every point in the domain that I'm looking at. Okay, so I have two forms of equations now. I have integral form, I have a differential form. These are the primary forms of the equations that I'm looking at, and I would like to solve these equations based on the numerical method that I will be looking at. Okay. Now, if you now we have understood, we have seen, or we have had awareness of what these governing equations look like. Okay. Now we would like to understand what is the nature of these governing equations. Now you see that every equation has dou by dou t term, which is a quantity which is varying in time. That means they are unsteady in nature. And you have the second term in the momentum equation, which is something like this, which is called divergence of momentum. Basically, this is a nonlinear term. To understand nonlinear term, I have this integral over here. If you see in the bottom, I have u dou u by dou x, integral u dou u by dou x. The quantity multiplied by its derivative there. So you know that such kind of integrations can't be easily integrated, okay, unless you know those parameters well. nonlinear terms are not easily integrable. So you have a nonlinear term sitting in the momentum equation, and they have this mixed parabolic, hyperbolic in nature, elliptic in nature. So what happens is, these in the first slide when I showed the governing equations, I showed that all the partial differential equations can be classified into three different forms: elliptic, hyperbolic, and parabolic. So each form has its own methodology to solve. Okay, there is no unique methodology to solve all those equations. So each form will have different methodologies. The beauty of fluid mechanics is governing equations will change its nature from elliptic to parabolic to hyperbolic based on the flow regime it is there. So suppose my fluid is accelerating from subsonic to transonic to supersonic to hypersonic, then what happens is, initially it is parabolic, then it goes to hyperbolic, and it becomes strictly hyperbolic in one of the regimes. So suddenly it changes. Dynamically it changes the nature. The nature of the governing equations dynamically changes. So suppose a certain phenomena becomes more prominent than the other phenomena in the governing equations, then it will change its characteristic. Like if my only heat transfer is more prominent, then it becomes elliptic. So those equations become elliptic. So you see that the form of the governing equations change from hyperbolic to elliptic to parabolic dynamically inside the governing equations. And the most complicated situation that you get is because of the nonlinear terms that are available. So the major culprit and the most annoying thing that you see in any fluid dynamics phenomena and people fear is the nonlinear terms. And these nonlinear terms are the basic terms which causes the turbulence, which is causing all sorts of nonsenses in a given fluid flow. So we'll not go into deep of those things, but as and when you go deeper into this, you'll understand why those things happen like that. Okay, so now I have seen a governing equation, its different forms, and I also had added physics to that and made those governing equations classified into this. So to avoid all the complications, I will make it very simple. So all the governing equations that I have shown is written in 14. So this one equation represents your mass, momentum, and energy conservation equations, all three, where U represents a vector, something like this. So the first element of U is density, the second one is momentum, the third one is total energy. I'm rewriting in terms of vector forms. So if I want to understand the nature of the governing equations, it is very easy for me to look at these kind of simplest equations and then try to understand the numerical methods available based on the classification of these equations. So I can simplify these equations, simply write, it doesn't simplify, it doesn't reduce the number of equations, but it reduces the form in which it has been written. That's it, nothing else in this. So these are basically the mass, momentum, energy equations and the associated mass flux, momentum flux, and energy flux that are available in those governing equations. Okay. So now there are two things that we have done now. The first thing is we have seen what kind of flows, what are the classification, different behaviors of the flows. We have seen different kinds of equations matching those particular flows, and we would like to look at what happens in a given simulation process. So let's look at each simulation process. Every simulation process will have a geometry associated with it. Okay. So first thing that you need to look at is build a geometry. So first you build a geometry. The second aspect is you understand the physics of that from the governing equations. You discretize the geometry. That means you break the geometry into small elementary pieces. Okay. So this is what it is. Say suppose you have a birthday party that's going on and you have a big cake that is available. How do you eat that big cake? You don't swallow the entire cake as it is. You cut that cake into small pieces and then you eat the small pieces as many number as you want. Similarly, the entire geometry is cut into smaller pieces. So either you define points or control volumes. When this process of discretizing geometry into control volumes or points is called grid generation. So once you get the boundary points, we term it called as a mesh. And we say that these meshes at these points, you want to solve the governing equations. See, your governing equations are valid at every point in the domain. If you consider a domain, how many points would be there? There will be infinite number of points. So you can't solve all those infinite number of points. So based on the availability of the resources that you have, you discretize the points to certain number of points, restrict your computations to certain number of points, and then solve those equations at those number of points. You define boundary conditions, and this setup, this discretization process, physics, and the boundary conditions, you give it to computer. Computer is a master in churning numbers, so it keeps on churning numbers, and finally it throws some data out of all those values. Now the data is obtained at those points, and you would like to look at how the data is behaving based on the conditions that you are giving to the computer. See, one thing that you need to understand is, whatever you give input, based on the input to the computer just churns the number and gives it back to you. So if you give a meaningful input to the computer, you'll get a meaningful output. Otherwise, you don't get you get garbage. So garbage in, garbage out. Meaningful, proper input, and you get proper output out of that. So in the process, what's happening, and we'll see now exactly. We'll see what CFD does right now from here. Okay. So we have different. We have seen that the flows can be categorized based on as laminar and turbulent flows. So categorized with different categorizations. So in fluid flows, we have the following basic equations. We can solve laminar flow as it is. Then you have turbulent flow simulations. In the turbulent flow simulations, you have different categories called Reynolds average Navier-Stokes equations. I'm not going into deep of these equations as such. We have larger simulations. We have direct numerical simulations. So you can see the problem and the complexity of the running of these equations in the triangle here. So if you want a very crude way of looking at a flow field, then we'll use RANs and the unsteady RANs. Then the next stage would be larger simulations. The peak, the ultimate is DNS simulations. Now, what is the difference between this? You can see on the left side, you have 3 jets that are coming from the simulations. So this is a jet that is coming out of a pipe. So imagine that you have your motorbike. When you start your motorbike, you see that the exhaust gases are coming from the muffler outside, from the silencer. So if you look at that gas that is coming from the silencer, that is a kind of jet that you are looking at. Okay, if you are carefully observed how the black flume that is coming out of jet, you'll see that it has too many structures in it. So if you simulate using RANs, you'll see the flow fit is something like this, which is in figure C. So you'll see that the structures are not that clearly visible. And if you use LES, you'll see that certain structures are visible. And if you see, if you work with DNS, there's a huge resolution. It actually mimics the flow problem. You'll see that DNS has a huge computation power. You need a supercomputer to solve it. Without supercomputer, you can't use DNS. At least a degree of high-end systems you need to use to get RANs. If you have only desktop systems, then you can only use RANs methodologies to simulate that, and that will take some amount of time in simulating these things. So based on the methodology, that though you have defined everything correct, if you don't have the proper computation power, that is the computer, the main tool that you have, based on the availability of the tool that you have, you can use RANs, LES, or DNS methods. Okay, so this is where computer and the software coding part will come into picture, and the effectiveness with which those codes have been written or the equations have been translated to a computer where it can churn out the numbers. Okay, so these are the different methods that you will have. And as I said, the model you can see here, this picture also defines this. RANs will give you a wake region behind the cylinder, but you don't see any separation regions or clearly. Unsteady RANs will give separations, but it doesn't resolve the eddies properly. Hybrid RANs and LES will resolve, but it is not that great. LES kind will resolve most of the eddies, but it doesn't resolve every structure in the flow field. Whereas DNS will give you the complete picture out of it. So if you want to get the complete picture of a given system, you should do DNS, but supercomputer and a highly effective code, and it will take long amount of time to get your results. So if you want results very fast and you want to see that, okay, this is the roughly idea how the phenomena that is happening inside the fluid, you can do RAN simulations and then get satisfied with that. So based on the availability of the tools, you should be able to look at the complexity of the systems that you're looking at. Okay, so now we have seen the physics, the mathematics part of it, the tools part of it, availability of tools. We look at the actual methodology with which these methods are solved. So all the equations can be solved within these three, majorly classified with these three systems called finite difference method, which is one of the oldest methods of numerical simulations. Then you have finite element method and you have finite volume method. Okay, so what is the difference between these three things? So suppose I have a domain and I take 3 points in that domain. When you choose certain number of points, this particular thing is called stencil. And if you finite difference method, what it does is it actually solves at those 2 points. In 1D, you solve at those 2 points all the governing equations. You transfer the governing equations to difference equations, and you solve the difference equations. So you have points. You will solve at points. In 1D, you have points like this. In 2D, you have something like this. In 3D, you can extend it in the other dimension. Okay, so you can put a layer of such cells points, and at every point you are solving in that. In finite element method, what you do is you connect the elements and you say kind of interpolate the data between. So in finite difference method, the basic difference which comes from finite difference method and finite element method is, in finite difference method you solve at only that particular point. In finite element method, you create an element between these 2 points, and you say that how do I interpolate the data between those elements? So you kind of create a structure, a polynomial, and you try to interpolate the data. You solve at those data points and interpolate data. Both are clubbed in the same equation. So that's finite element method. It's simply stated finite element method. Finite volume method, you consider a control volume around a grid point, and you try to conserve all the quantities in those grid points in that particular volume. So this is finite volume method. So finite difference method, you are only dealing with points. Finite element methods, you can create structures, and the interpolating strategies that are available inside the method determines the accuracy with which the method is being you get a solution out of it. And finite volume method, you create a control volume, small control volumes around each point. So at every point you have to create a non-overlapping control volumes, and then you solve the non-overlapping control volumes, the governing equations at those points. Let me explain you with a simple example. So suppose I am solving this equation dou f by dou x is equal to c. Okay, so in finite difference method, the first dou f by dou x is written in difference form. So dou f by dou x is approximated as del f by del x, which is written in this form, and then you solve this equation to get at every point in the domain, and you get the value of f. Okay, so that is finite difference method. In finite element method, you kind of do certain kind of as I said, you kind of do interpolation strategies. So the interpolation function is kind of known as a shape function. You transfer your domain, the gradients, to the known shape function, and then you solve it. So you do that in finite element method. In finite volume method, you take the volume as it is, you integrate that governing equation in that particular control volume, and then you solve it. So this is the primary difference between finite difference, finite element, and finite volume method. In this presentation, I primarily have chosen to work with finite volume method. In a finite volume method, as I showed the governing equation previously, you take a control volume, and you assume that in the control volume the fluid property remains constant, and you try to integrate that particular thing. So you kind of calculate fluxes on the interfaces, add those fluxes on the interfaces, and evaluate the time variation of that quantity inside the control volume by adding those fluxes. Okay, so this part would be a little bit advanced for the newcomers. You should bear with me for some time, because it'll actually, we are going to a little bit of details of what finite volume method is. So what you do is you are actually calculating your governing equation in this control volume A, B, C, D. So the mass, momentum, and energy are varying at that point, which is called centroid. And to calculate that variation at that point, you need the fluxes at the surfaces at these normals, ends. These are the unit surface outward normals that are available at the surface. You calculate the fluxes at all the four faces. You add up all those things, and that would give you the actual variation of that particular quantity inside the control volume. So this is the basic idea of finite volume method, and you can see the equation in 22. Okay, how do you do that? So you have this basic governing equation. So now you see that there are certain quantities which are varying at the cell central. So if I go back to my figure, there are certain quantities which are varying at the centroids. There are certain quantities which are moving in and out through the surfaces. Okay, so you have to balance these two things. This is the balance that you do in all these methods. So I'm rewriting this equation 22 here in 23. So you can separate the quantities which are varying in time. You can separate some quantities which are varying in fluxes. So dou u by dou t, this quantity only varies in time. It doesn't vary in space. And R, which is called residue, which is nothing but the summation of the fluxes from all the surfaces, is varying only in space. So you don't need time there. So you can actually strategically divide these two things separately. Use separate methodologies to discretize spatial quantities and time quantities. That's what we are going to do here. So approximate the derivative of time, and you transfer that values. So this is, if you are doing only the time, if you don't want time accuracy, you can do first order Euler time discretization methodology. Method. So I'm just showing you the third order method. You can have fourth order method or fifth order method of Runge-Kutta method, whatever it is, time discretization, explicit nature. So here, these are the ways in which the time discretization strategies has been taken care. Okay, now what after this? So once the time discretization is done, you have spatial discretization. Spatial discretization can be taken care. I would not like to spend in detail discussion here. So saying that I want to calculate the flux at the interfaces. Flux as an interface can be calculated in two different forms. One is central scheme, the other one is upwind scheme. Central scheme, say suppose I have an interface, say suppose I have 2 points, j and j plus 1, and there is an interface sitting in between that. And the flux is transferring. So as the flux is transferring, I want the interface flux. So the flux that is coming from the left hand side is given as FL, and the flux from the right hand side is coming from FR. And I can use these two as an average flux and dissipative flux. And or I can calculate FL plus and FR minus separately, and I can add them separately. So based on the numerical scheme that is available there, you can actually calculate the fluxes in different ways. But you can ask the question, how many kinds of numerical schemes are there? Is there any unique way of doing it? There is no unique way of doing it. I'll show you a list of schemes that are available. So these are the list of schemes that are available for each of the problems. So you have a central scheme, the list of central schemes. This is only a partial list that I'm showing here for both the central schemes and upwinding schemes. I don't want to go in detail of every scheme, because if it goes, each scheme will take 1 hour of lecture. So you can imagine how much depth you can go in understanding those schemes. So you can either take central schemes which are directionally independent and upwind schemes which are directionally dependent, and you can actually club the schemes to get the fluxes. So you use these schemes to get the fluxes. And that is for viscous inviscid fluxes. Viscous fluxes, what do is, for each, if you want to find a gradient on the face, you need to construct a control volume across the face. This is called co-volume method. Use the Green-Gauss-based method, divergence theorem, to calculate the fluxes over the face. So this is how viscous fluxes are calculated. So you have inviscid fluxes, you have viscous fluxes, you calculate it. You use these methodologies to calculate it, you sum it, and then submit it. Okay, so fine. So I have done time discretization, I have done the spatial discretization. So what's the problem with these methods? So there are certain physical, unphysical phenomena that occurs for different methods. These are the popular schemes, phenomena which are not physical in nature. They come because of the numerical approximation. See, whenever you are doing numerical method, you are doing some certain kind of approximation. So whenever you are doing certain kind of approximation, you see that there's a certain phenomena that comes out of it. Okay. because of this approximation. So you have non-smoothness, you have unphysical shocks. You don't predict the values. Say suppose in the first figure you have an expansion shock. So that's unphysical. Okay, that for a regular perfect gas equation, that's an unphysical in nature. So you don't want that in your numerical simulation. If you get something like that, it is not valid solution. And there's a second scheme. So you have a Steger. If you use Steger-Norman scheme, the internal energy may be predicted like this. The actual internal energy should be like this, the solid line. But that scheme predicts something like this. So you can see the difference between the internal energy of these schemes. And there are certain places where you find oscillations in the schemes. So these are unavoidable. So these issues should not be avoided. So we should be able to. That's the reason. So if you are trying to balance a particular thing, something else pops out. So you have to see that everything gets balanced and see that you actually solve these equations step by step. Okay, in a manner where you get physically realizable solutions. Okay, so that's where you have so many schemes that are available, and still the design of algorithms are happening. Yeah, so we have done with this. What we do is we have seen certain methodologies where to solve it. So you give this, you write, you have these methodologies. You write a code and submit it to a computer. So the computer will generate data. Okay. Now what will you do with the data? And that you have to post-process the data, and that process is called post-processing. Okay. So in the post-processing of data, what will you see? So you have data now in your hand. You can create a line plot. You can that is shown in figure 1. That's you can point at a given point. You can plot how is the variation of density, pressure, temperature, and all the stuff. That's called line plot. You can have contour plots. So there are two kinds of contour plots: field contour plot and line contours. So if you see the second figure, you see that there's a shock wave that is propagating from the diverging section from the 90-degree point at a corner. So you can see an expansion fan, a contact discontinuity, then a shock traveling. All these things are represented properly from the contours that your data that you are looking at. Third one is a stream vector surface plots. You can also have streamlines. You can plot streamlines. You can plot vector plots. You can show the vectors how they are changing. You can show the surface plot. The plot that you are looking at is you have a bubble in a liquid and it suddenly bursts. So if it suddenly bursts, what happened to that surface in that area? So that's a plot that you are looking at in the surface plot. So you can represent the data in terms of line plot. So how meaningful you represent the data is important. There are certain points I can only finish off with the line plots where I don't need contours as well as surface, useless. So there are certain places where I need to understand. So if I plot, if I draw a line plot on this second surface, you don't see the beauty of how the shock waves are evolving, how the expansion is evolving, and all this stuff, these things. So at those points, you need to understand that 2D surface plots are important. So suppose in the 3D phenomena, if you draw only 2D points, then it doesn't make sense. So at that point, you need to show the surface and see how it is evolving. Time evolution. You can also look at the time evolution of all these things as seen in the animation. So all these things will come under the post-processing. So with this, you can see that there are different steps that you look at. First of all, you need to understand what is the physics that I am trying to understand. Then you have to construct the experimental setup. So you have to create that experimental setup. Okay, which is kind of geometry creation and boundary conditions. What actual boundary conditions I need to give, and all the stuff. Then what you do is you need to choose proper governing equations. So what governing equations? Can I solve Navier-Stokes equations for all the problems? No, not needed. For heat transfer problem, I'm just only looking at temperature variation in a steady state temperature in milliard. I don't need Navier-Stokes equations to solve. I can just finish off with a Laplace solution of a Laplace equation or a Poisson equation. So I don't need to worry about solving Navier-Stokes equations every time. So what governing equations I have to choose for the problem? Then what discretization strategies I have to use? So that discretization strategies comes on the fact that if you have a complex geometry, then you can't apply finite difference method. You can only apply with finite element and finite volume method. If you have a simple geometry, then finite difference method is sufficient enough. You can get higher order beautiful results with the finite difference method. The geometry is simple and the governing equations are simple enough. Then if you have a very complex geometry, then you can use finite method. But finite element method has its own restrictions of accuracy and resolving shock waves, like properly resolving shock waves and contact discontinuities. So if you want conservation preservation schemes, the governing equations that I've shown you are basically in conservative form. Okay, so when you are looking at in conservative form, certain phenomena is conserved. So if you want to resolve this conservation, then you have to solve those equations in finite volume method only. Finite element method may not preserve the conservation there. So based on the properties that you would like to explore, you need to choose the governing equations, you need to choose the physics. Once you choose the physics, you need to choose the numerical methods. Once you choose the numerical methods, what are the numerical schemes that are available, which gives you accurate and with what accuracy those numerical schemes will resolve the solutions. You need to understand that. Then you need to choose a proper system to solve these equations, and then you need to look at what are available tools, codes. Then here it comes saying that should I write a code, or should I use existing code? Then we have the other aspect that comes here. So we have open source tools like OpenFOAM, SU2, HiFlies, BOSS. BOSS is a spectral solver which is similar to finite element method. OpenFOAM, SU2 and HiFlies are basically freely available codes which can solve any fluid dynamics problem. You don't need to pay anything. You don't need to pay a single pi for this. It's free, entirely free, available for all the users. These are the existing tools that you are. Suppose you are not satisfied with the numerical methods that are available in that system. Either you can understand the code and modify that, or you can rewrite your own code. So that's the whole point that people look at it. So I don't want to fiddle with writing codes. I don't want to waste my time there. Use these codes. You don't need to spend a single pi out of it. These are the solvers that are available. And suppose you want to visualize the data. What are the softwares that you have? Here also you have open source data. You have ParaView, you have Mayavi, you have GNU-plot, you have Python. In Python Matplotlib, you can use Matplotlib to visualize the data. So once you set up your experimental setup, then you understand. You say that I'm not good at coding. I'm not interested in it. Then you take some other's code. Try to understand how the input should be given to that code, how the output should be given, and what is the form of output that code gives back, and then modify a little bit to say that to understand your results. Okay, so these are the open source solvers that are available. Open source data visualization. Similarly, open source mesh generation softwares are also available. I strongly suggest you encourage the students to venture into these things. You don't need to sit and write the codes. The codes are already available with LES. Some certain places you have DNS codes. Not all DNS codes. This OpenFOAM and SU2, you can go up to LES methods. DNS, of course, you need to spend some time, and you need to have a supercomputer for that. So you may not be able to get a free software out of it for DNS. For that, you need to write your own node codes. So these are the available softwares that are available to solve the problems. So now it's up to the user community to decide what to solve, how to go about reading things, and all this stuff. I think I'm done with here. So to wind up the lecture, we have seen that what kind of flow features that we have. Then we have looked at a little bit of mathematical equations that govern equations. How do they look at, and what are the kinds of discretization strategies that you have. Then we saw the process of how to set up an experiment and then conducting an experiment. Then we saw the results, the issues with the existing schemes that are available. And we saw what are the available softwares that you can use for CFD solutions. And then we saw what are the available tools that you can explore, which are free for everybody, and that is available in open market in the CFD list. This also happens in finite element softwares also. I just shown you certain softwares which are used for only fluid flows. For people who are interested in structures, designing structures, analysis, they can go and explore the corresponding softwares. So I'll stop it here, and if you have any questions, I'll be happy to answer. Any sort of questions, don't hesitate to ask.
Thank you very much, Dr. Ramesh. It is Sadan Kumar.
Hello, sir.
Yeah, so it is very nice, and I'm thankful to you. Such a marvelous and lucid lecture you have given on this topic. I believe the students are more than happy. Yeah, really. I mean, definitely, if they have some queries, they will ask. Actually, they had some examination.
Oh, okay.
Examination is going on. So they may not be able to ask the question, but even though if anybody of you are interested, then please ask. But I'm saying really, it is really superb lecture you have given. I'm very happy.
This is a basic introduction. There is a glimpse of
that's what it was needed. This type of lecture was needed for the students.
Yeah.
And I will hope in near future, whenever we find some time or students want, we will again interact.
Sure, sir. Sure. Anytime. And people, I think my mail address is there. If you have any questions, if you have any doubts.
Yeah. We can post also.
Yeah.
Rishikesh?
Yes, sir.
If people are in, then you can collect the question and we can post the question to Dr. Kumar. And then he will give the answer in detail.
Yeah, sure, sir.
Right?
Yeah.
Yes, or if anybody wants to right now also, one can ask 1 or 2 questions right now. We can also take.
If anyone wants to ask any questions, they can unmute themselves and ask the question right now.
Yeah. Otherwise, we will send.
Yeah. Good evening, sir. This is Prashun here.
Yeah, Prashun, please.
Yeah, sir. Actually, I read somewhere. I was reading a book a few months ago, and I get to know that Navier-Stokes problems is one of the 7 millennium problems of Clay University. So,
yes.
What is that, sir? Actually, I wanted to know out of curiosity.
Yeah.
Like Navier-Stokes has been with us like from 19th century itself, but still we don't have a unique solution of that.
Yeah. So as I said, while I was showing the presentation, I said there are nonlinear terms that are existing in Navier-Stokes equations, which creates a lot of trouble. So Navier-Stokes solutions are not one single equation. It's a set of equations that I showed you there. So those solutions, they don't have a unique analytical solution. There's no one solution for that. Because you have seen the introduction, how many kinds of flow features are there? For all kinds of flow features,
yes, there is always some kind of turbulence in the equation. Yeah.
So irrespective of whether it's turbulence or laminar or whatever it is, Navier-Stokes represent all the forms of such equations. Everything is embedded in the equation, but you can't solve them analytically. That means you can't integrate them analytically and give a solution out of it. You have to definitely do only numerical methods. That's it. For very few simplest cases, you find analytical solutions. But that is not unique for that. That is only there are only particle solutions. So when you do M1 in your solutions, you have particular solutions and generalized solutions. You might have studied that. So when you do Navier-Stokes, when you try to solve Navier-Stokes equations, you don't have generalized solutions at all. You can't get it.
Yes, sir.
People are still trying to crack that with different methodologies, different tools available to get that problem solved. But it is still a question saying that people are not they're attacking the solution and then they're finding it different. And I'll quote here at this point. Many people have attempted to solve Navier-Stokes solutions. They gave up in their life and they started doing something else and they got Nobel Prizes in those other fields. This is true.
Okay, sir.
This is a fact. You can check it out. Many people many Nobel laureates who started off saying that I can crack the Navier-Stokes equation, ended up into Nobel Prize in some other field, because the knowledge that they gained here, they could apply it somewhere else, but they could not crack Navier-Stokes equation. Yeah. But numerically what we are saying is, we are trying to give up a hope, saying that you can solve these equations and get some solution out of it. And we are not saying there's a unique way out of doing it. As I said, the number of schemes that are available itself shows that there's no unique way of defining a particular quantity, because you are trying to approximate it. Approximation can be done in any number of ways. And you're looking at the simplest and the best approximation that we are trying to look at. So,
So it's going to be one of the millennium question for quite a long now.
no, it will be forever. Take it for granted. Unless you invent a new mathematics tool,
Yeah, yes, sir.
you
Yeah.
may not be able to solve Navier-Stokes equations. That's for guaranteed.
Okay. Thank you, sir. Thank you for the clarification, sir.
Yeah.
Yes, sir, this is Rishikesh.
Yes, Rishi.
Yes, sir. Since juniors are there, sir, I would like to know some engineering problems where CFD can be utilized in some project work, which may be beneficial for the juniors.
You can take any problem. So suppose if you are looking at external aerodynamics, like shapes of the cars, buses, or trains, objects, anything. You want a fluid flow information. You want to construct bridges. You need to look at airflow and airflow analysis out of that, because wind forces are important. To take wind turbines, you need fluid dynamics into comment. So fluid dynamics, wherever the object is surrounded by fluid and it is moving, fluid dynamics is important and it plays a major role. Now imagine that place where object is not surrounded by a fluid. On the earth, in the atmosphere, there is no object that is not surrounded by a fluid, whether it is air or gas or liquid, any kind of liquid, it is surrounded. Your body is fully surrounded. So biomechanics, you need fluid dynamics to understand what's happening. Certain diseases that are coming is because of the blood flow patterns that are happening. So people are studying blood flow patterns in the nerves. So as the blood flow patterns are happening, it is a viscoelastic material. So as the fluid is happening, we engineers, mechanical engineers, our pipes and structures are rigid. They don't expand, contract. Whereas these veins, they expand and contract as the fluid is moving at a high speeds or low speeds. So you should understand what's happening there, and it's a non-Newtonian fluid there. I haven't covered the Newtonian and non-Newtonian part as such. So based on the fluid that you're looking at, based on the object that you're looking at, you name a problem where fluid is not surrounded by the object, we can say that fluid mechanics can't be applied there. In this universe, every object is surrounded by fluid that is moving. So fluid mechanics is there, and CFD can be applied there.
Sir, any software which you'd like to suggest for starting CFD?
I suggested, right? OpenFOAM is there, SU2 is there, HiFlies is there. You Google open source, you just type open source CFD software, so you'll get a list of people. Many people have written their codes and given to public saying that you can utilize this code for free. I think my code is also available there. So I written my own code because I developed an algorithm. So that is also left for free. So anybody can use it. There's nothing new in that. So there are a whole internet. If you Google, there are a whole host of softwares that are available for free, which you don't need to spend even a single pi, and it is for free. And you get support from them also. When you say that, if you want to discuss with them, there are lots of groups, people are discussing. They'll help you. The authors will help you. If you write to them, they'll talk to you. You'll get a whole host of domain that you can expand. That's one thing that you can look at it actually. So there are a few softwares that I told you as per the solvers, as well as plotting softwares that I have given. So yeah, there are infinite possibilities there actually.
Thank you, sir.
So Rishikesh, please propose vote of thanks to Dr. Ramesh.
Yes, sir. It was actually a very knowledgeable session, and I hope that students have learned a lot. So I'd like to thank you personally. It was very knowledgeable for me, being in the final year, since we have it as a topic in our study. And definitely when the students reach their final year, the juniors, they will at least have a summary of what they need to learn at that time, because basically whatever we study, I think that it has been covered in a very precise manner, I'd like to say, and I'd like to thank you for that.
I thank Dr. Shailendra Kumar sir for giving me this opportunity. It's my privilege to talk to students over here like this. In fact, because of this pandemic, we could not physically meet.
Yeah.
Anyway, the virtual platform has.
We will continue over the next time also. We will talk someday.
Sure, sir.
Yeah. Okay. So thank you, doctor. Thank you very much.
Thank you. Yeah.
Thank you, sir.
Thank you.
Okay, guys, you can start to leave this meeting now.
Fine, sir. I'll meet you afterwards then.
Thank you, sir.